All right, so today we're going to go over priority queues. Kind of like a queue, only you're going to have priority. Namely, let's say you have a queue of people, but someone needs to go up to the front, so they would have priority, obviously. So this is just an idea of how can we come up with a certain priority queue for different, I guess, tasks that might be out there. I gave the example of people in line or in a queue as one. And then after that, we're going to talk about Project 4, at least the start of it. I was able to at least get the main part of it started, so I can give you a preview so you can start thinking about it over the weekend. Because Project 3 is due tonight, right? Great. Okay, priority queues. Oh, it's going to be one of these slides. So stack is first in, last out. Queue is first in, first out, just like a queue or a line. So a priority queue, you can think of least first out, or the smallest element is the first one to be removed. This is defining the smallest to be the highest priority. You could also do largest out, which would then be the largest number has the highest priority, or is the first one to get out. When it comes down to it, the smallest is up to the programmer, or whoever has the highest priority is up to the programmer. You just have to somehow have an ordering to it, and you're good to go. These slides are for Java, that's why there's a comparator or comparable, but they work for C++ as well. Naturally, if there's several smallest elements, you can decide which one goes first. We don't care which one. They all have the same priority. You just have to make sure that all of them go before anyone else of a lower priority goes. All right. Now, this is actually an abstract data type, and I don't know if I've explained this too much, but an abstract data type is some examples we've done are stacks and queues so far. Let's see, is there another one? I think just those two. Yep. Because we really use a concrete data structure like an array or a linked list to implement them. So that's why it's abstract. It's not like we create the queue structure, so to speak. We use something else to implement it.
So there's like an array or a list behind the scenes or something?
Yeah, behind the scenes. And we're having an interface that you just adhere to, and we think of some type of data structure or data type. So the priority queue, same thing. I mean, the queue was an abstract data type, so now priority queue, same thing. Constructed, be able to add something, remove the least, get the least if you want to, if it's empty, and then possibly the size. So the interface is actually pretty simple. So we need to think of a data structure. Before we do that, quick example on the board. All right, give me some numbers. Love numbers.
4,
7,
9,
13.
9,000.
All right, let's something in between this range.
8.
8. Okay, good. All right, perfect. So if this was a priority queue, which would go first? 4. So the 4 would go first, then the
7,
all right, then the
8.
8. So then the 8 would go first, then the 9 and the 13. So notice that they did not necessarily do first in, first out here because of their priority. All right, good. So we need to choose a data structure for this. If we do an array, load the array once with the numbers and do a lot of searches on it, we want to make the searching fast, so we probably want to sort the array. So if you want to sort the array, if we load a huge array and only expect a few searches, you probably don't want to spend a long time sorting the array. So the idea that what they're trying to say here is, you have a huge array and you're going to do a lot of searching or a lot of hopping, or dequeuing, I should say. You probably should sort it because then you can do a binary search to find the right element. Of course, sorting is in log n, so that does incur a little bit of a penalty. And in reality, with a queue, especially a priority queue, we eventually remove everything that we add. So we're going to be doing a lot of searching, is what it comes down to. The other problem is with a queue, you're going to be adding elements at certain points in time as well. So you're going to be adding and removing back and forth. The point of this slide is that you can't just evaluate add, you can't just evaluate remove. We need to look at the timing for adding plus or remove. So we're evaluating add and remove together is what we're looking at. Does that make some sense why we need to do both in this case? Because it's an online algorithm, meaning that you're going to be adding and deleting dynamically. Like, it's not like you add all the elements and then you just remove them all. It's you add a bunch of elements, you remove one, maybe two, add another one, maybe remove one, add four, remove three, add two, so forth and so on. So we really want to evaluate adding and removing here, not just one or the other. Okay, so let's go ahead and look at the array. Whoops. We could do it as an unsorted array with a count of elements. If we did that, what would be the big O of adding an element? O of, well, what's that?
O of n squared.
O of n squared, okay. Throwing names out. What do we have to do if we're just adding it to an unsorted array?
Unsorted? Oh, you just added it the position of m size.
Yeah, you just add it to the end. And if you have enough buffer there, that's O of 1. But if you need to resize it, then it becomes
O of n.
O of n. So O of 1 on average, maybe O of n if you need to increase the size. Okay, whoops. How about removing an element? Why?
Because you're searching through the array, and then if you find it, you remove it.
Right, you have to search through the array, and then once you find it, you actually have to shift everything down as well. So it's O of n plus O of n. We'll just still just O of n. And then what was the last thing? Oh, okay. Hence, adding and removing is O of n. All right. So O of n, or at least we got a baseline of what we need to look at here. But yeah, this is not efficient at all. We could do it with a sorted array. How long would adding take in a sorted array?
In logging, we did binary.
Oh, no. So the array's already sorted, and we're going to add one element. So how long does it take to find the position?
In
Log in.
login.
Log in, because we just do a
searches.
yeah, log in. Binary search, just log in. Welcome. Yeah, thanks, Jonah, for increasing the class size by 50%.
All right, I got you.
You always coming back, even though it's 20 minutes late.
Sorry.
All right, so finding its log in, but adding is still O of n. Why?
You gotta shift everything up.
You got to shift everything over, which can be O of n. Yeah. How about removing? Well, you got to find the element, which is
Login.
log in. Of a sorted array, finding an element, log in. But then why is it, well, that's not true. Why is removing, oh wait, no, removing an element O of 1, actually. Actually, removing the element is O of 1. I take that back. Because if you're trying to remove, let's say, the smallest or the largest, where is it? Beginning and the end. And hopefully you make it so you just decrement the size to do it, so we make that O of 1. Yeah, so removing in this case would be O of 1, but that still means adding and removing to an array is O of n time. Okay. Again, this is inefficient. How about linked list? Let's see if it does any better. What if we use an unsorted linked list? How long would it take to add an element to an unsorted linked list? Unsorted. Unsorted. Where would we add it if it was unsorted?
Oh, just add it to the end.
Yeah, which is
Just
O of 1. All right. Oops. We'll just give you the answers. Why is removing element O of log n?
we have to find it.
You have to find it, so you have to look through the whole thing. So adding and removing becomes O of n. Oops, okay, we'll do it that way. How about a sorted array? Well, adding is O of n, why is this?
Because you have to find where to put it.
Yes. Well, why was an array log n?
Because an array, you can divide it in half.
Yeah, but it's still O of n because you had to shift everything down. So this you can't do the binary search, but you still have to go through the whole thing, so it's O of n. How about removing?
Oh, then.
It's sorted. So where is the element you want to remove? at the end, which makes it
Oh, one.
O of 1. All right. So again, adding, removing O of n. All right. So linked list isn't going to help us out. What's our next data structure? Binary tree. All right, Jonah's on top of this. See, he was good job. All right.
We're doing.
How long does it take to add something to a binary search tree?
Log in.
Okay. Log in to O of n. If it's not balanced, why could it be O of n?
Because there's a possibility it could be a linked list.
Right. All right. How about removing?
Log in.
Yeah, log into O of n again. Again, if it's a linked list, you have to go down the chain, right? How about a balanced binary tree? How long does it take to insert?
Log in.
Destroy it.
All right. But are complicated. So actually, a binary tree is not a balanced binary tree is not a bad implementation, but it's going to get complicated. Hopefully, you've all recognized this by doing project 3. Everyone see that? That are complicated now makes sense.
Yeah, the APL does it weird.
Yeah, it rotates, right?
Yeah, like it has it to where like it will do the left and then the right, like in two different functions.
Yeah. Well,
Where'd you find it?
Huh?
Where'd you find it? Was it like Geeks or something like that?
I think so.
That's where I found it.
Because they had like an actual thing where you could like go and like test it to see it run.
Oh, really?
So I went to it and I watched it run and how it did stuff.
yeah, AVL I recommend it because there's so much data out there for AVL.
Yeah.
Okay. Yeah. Well, the AVL was okay. Let's just get a simple algorithm that balances a binary tree. So they just broke it up into, I think it's like 2 really basic rotations, and then you have the advanced rotation does something and then calls the other rotation.
Yeah.
Yeah, and then you're done. Yeah. Which I mean, that's if you look at the other ones,
Yeah.
you're still good to go. All right, guys. So we're gonna say the binary tree is not quite what we want. What else could we use?
Try a heap.
A what?
A heap.
A heap. All right, let's look at a heap.
I'm just going down the line of ones that we've done.
You're doing great. You're doing great. What would be the insertion or adding time for a heap using a priority queue? Because a priority queue, your heap property would just be either the highest or the lowest, right? So you still have that going on. So how long does it take to add something to a heap? Well, you add it to the end, and then you have to sift up, right? How long does it take to sift up?
Login.
Log in. All right. This is large. Oh, okay, we're going to have some pictures about a heap. How about that? Nice. So you see 12 and 3, added the 3, so now we got to shift it up to get the heap property. That looks great. Okay, last index 5. Wow, we're just going to talk about heaps again. Okay. All right, to add an element, increase it, reheap. This is called, well, they call it upheap bubbling, percolating up. I call it sifting up. Well, these slides. So it requires log in time. How about removing?
Oh, one.
Well, you can, what did you do? You remove the first element, and then what did you have to do?
You have to sit down.
Well, you had to swap it with the last, and then sift down. And that was a login operation. I feel like I need to teach Big O better.
It's so good.
No, there's just so many of them.
There's so many of them?
Yeah.
Oh, wow.
There's just a lot.
Okay. All right. All right. And then you have to basically sift down, percolate down, log in. Thus, it's log in to add and remove an element. All right, guys. When we do our priority queue for our lab, which data structure should we use? Louder?
The heap.
Okay, good. This is surprisingly not that bad. I don't know if I agree with that bullet.
Yeah.
A heap is a vector that has been heapified. So you make heap to heapify a vector. Cool. Further pushes and pops should be done via heap functions. And then push back plus push heap and then pop heap. In other words, if you're going to push to the heap, you push back just like a vector, and then you call push heap, and it does the sift up. If you want to pop from it, you do pop heap, which removes it, and then does the switch and sifts down. All right? I'm telling you all this because this is going to be one of these labs where I'm going to do no coding for you, but you're going to have a lot of time to figure it out yourself. Some example code would definitely help. So, before make heap, you've created the vector of all the different elements. Then to make it a heap, or to heapify it, as I like to call it, you do make underscore heap, the begin and the end. So it's going to make a heap out of that range. Then you can see what the max element is by calling dot front. To push something onto the heap, you do dot pushback, 50, or the value, and then you do push heap. So notice you're calling the vector first, and then you're calling the sift up next. Then you can display, and then you can use pop to just remove the top element, and then you're done. All right, everyone good with this? I don't think it's too well, that actually makes it seem not that complicated,
Yeah.
which is great. And apparently we forgot to put the top line of code up there, so you knew that was initialized vector. Isn't that great? Okay. So after this line of code, what's in the front? What should this display?
40.
40, right. You add a 50, push the heap. What should be displayed here? 50, right. Pop the heap. What should be displayed next? 40. Okay, good. Everyone good? All right, we'll just have some weird slides going on today. That's fine. Make heap, heapifies. Remember, if you're going to add to the heap, you have to push back and push heap. So it's two function calls you must perform. Then you can push heap, you can get the front, you can sort the heap if you want to do heap sort. Bet you would have liked that earlier.
Would have been very helpful.
Is heap can tell you if you're still a heap. And yeah, is heap until just tells you what part of the heap you still are a heap. All right, heap, heap, heap. Comments. Let's see what comments I have. Priority queues data structure is designed to return elements in the order of priority. Great. Efficiency is usually measured as the sum of the time it takes to add and remove the element. Simple implementations take O of n. That included our array, both unsorted and sorted, and our linked list, both sorted and unsorted. A heap implementation takes log of n time. So for any sort of heavy-duty use, you want to use a heap implementation. Really, a heap right now was basically created to do a priority queue from what I've read. I mean, it'll do other things really nice, but it really fits doing a priority queue very well. My recommendation? Oh boy. If you need a priority queue, define it as an ADT. I do not recommend, well, whatever. Start with simple, keep the implementation hidden so you can change it later. All right, later. Whew. The end. All right, guys. Really quick presentation today. Any questions on that? Everyone ready for the lab? Sure? Okay. All right.